Welcome to the Deep Dive. Today, we're looking at something fascinating, AI agents. They're getting pretty autonomous, right? Doing complex stuff, scientific research, software engineering.
Yeah, absolutely.
But it makes you wonder, how good are they really when you put them up against something like cybersecurity? Hacking, defending. Can they actually handle that level of complexity?
That's the million-dollar question, isn't it? And honestly, testing them properly has been, well, tricky. A lot of the older benchmarks were too simple, like little games, small bits of code, not the real world.
Right, not the messy reality of huge software projects. And that's exactly the gap this new framework CyberGym is trying to fill. That's our focus today.
Yep. We're going to unpack CyberGym, look at how it works, what it found out about AI's current skills, the good and the not so good, and crucially, how these agents are actually digging up brand new threats.
So this is basically your shortcut to understanding the absolute cutting edge of AI and cybersecurity. Let's start with CyberGym itself. What is it exactly? And why now? Why did we need it?
Well, like I mentioned, the older benchmark Cybench, some CTF challenges, they were just too limited. Maybe a couple hundred tasks, tiny code bases.
Right.
Real software, it's thousands of files, millions of lines. So those benchmarks just didn't give us a realistic picture. It was a big gap.
Okay, so CyberGym steps in. How is it different? What's the scale we're talking about here?
Oh, the scale is impressive. We're talking 507 benchmark instances, and each one comes from a distinct real-world vulnerability.
Wow, 1,500.
Yeah. Found and fixed across 188 different software projects, big, widely used ones. So these aren't made-up problems.
And where did they get these real-world vulnerabilities from? How authentic are we talking?
They pulled them straight from OSS Fuzz. That's Google's big continuous fuzzing project.
Ah, okay, so fuzzing is like bombarding software with junk data to see if it breaks.
Pretty much, yeah. Highly automated. It finds bugs by throwing tons of unexpected inputs at programs. So these vulnerabilities are the real deal, found in code that's actively used and tested.
Okay, so authentic problems, big scale. What's the actual job they give the AI agents in CyberGym? What do they have to do?
The main task is to generate a proof of concept test, a PoC.
A PoC, right. Like the smoking gun that proves the vulnerability exists.
Exactly. It's a piece of code or input that triggers the specific vulnerability described. And the tricky part is the AI has to figure this out by looking at the entire code base. Could be massive.
Right.
Find the right spot, craft the PIC to trigger the bug right from the start of the program.
Okay, so it's not just finding a needle in a haystack, it's building the needle pusher too. How do they know if the AI actually succeeded? Just crashing the program seems too easy.
No, it's smarter than that. It's a two-part test. First, the PIC must trigger the vulnerability in the pre-patch version, the broken version.
Okay.
But then it must not trigger it in the post-patch version, the fixed one.
I see. So it confirms the AI found that specific vulnerability, not just some random other crash. Clever.
Precisely. It
Yeah.
validates they're targeting the right thing.
And who are the researchers behind this?
It's a team from UC Berkeley. Zhen Wang, Tianning Shi, Jingswan He, Matthew Kai, Jilin Zhang, and Don Song. And they've made the whole thing public code, dataset, leaderboard, so others can build on it.
That's great for transparency. And how are they measuring performance? What are the main scores?
Two key metrics. First, percent target vuln, reproduced. Basically, how often did it successfully create the PoC for the known bug?
Right.
And second, percent new vuln. Found. This is interesting. It counts how often the AI's PFA crashes the fixed post-patch version.
It crashes the fixed version, so that means...
It means the AI might have found a new bug, or maybe the original fix wasn't complete. So it's not just testing, it's potentially discovering.
Okay, that adds a whole other layer.
What?
So CyberGym is set up, it's rigorous. The big question then, how did the AI agents actually do? How smart are these AI hackers today?
Well, despite all the hype around AI, the initial results, they were pretty sobering. On what they call level 1, that's the code, plus a description of the bug. The average success rate for reproducing the known vulnerability was less than 10%.
Wow, less than 10%.
Yeah. And finding new vulnerabilities, even lower, below 3%. It really shows how hard these real-world tasks actually are for current AI.
Below 10% for bugs they were told about. That really puts things in perspective. What does it tell you?
It tells us this is not easy. Reasoning across maybe millions of lines of code you've never seen before, finding that specific flaw, crafting an exploit. It's incredibly complex, but there were some interesting differences between the AIs they tested.
Okay. Like they tested different types.
Yeah, 4 main agent frameworks: OpenHands, OpenAI Codex CLI, more general coding agents, and then Enigmo and the CyberGym agent, which are more focused on security, like capture the flag tasks.
And did the generalists or specialists do better?
Kind of depended on the task. The general agents, like OpenHands, were a bit better at reproducing the known bugs,
Yeah.
but the security-focused ones, Enigmo and CyberGym, were slightly better at finding new vulnerabilities in the post-patch code.
Huh. So maybe you need different AIs for different jobs, like one for finding known issues, another for hunting new threats.
Exactly. And what was really telling was the overlap. Different agents tended to find different vulnerabilities.
Oh, interesting. So they weren't all finding the same easy one.
Not at all. Very low overlap, which actually suggests their strengths are complementary. You could potentially use a team of these agents, each good at different things, to get much broader protection.
That makes a lot of sense. A task force of AIs. What about the underlying engine, the LLM? Did models like GPT-4 or Claude make a difference?
They did. Claude 3.7 Sonnet actually got the best reproduction rate, just under 12%. GPT 4.1 was next, around 9.4%.
Okay, so the top models did best. That makes sense.
But here's the surprising part. Models specifically trained for software engineering tasks, like one called SWU Gym 32B,
Yeah.
they performed really poorly, like less than 2% success.
Wait, really? The ones designed for code struggled. How come?
It seems CyberGym is just a fundamentally different and maybe harder challenge than what those models were optimized for. It's not just about generating code, it's about this deep, targeted security analysis across huge contexts.
Oh, that is counterintuitive. So what other factors made things harder or easier for the agents? You mentioned different levels.
Right. They tested how much information the agent got. Level 0 was just the raw code, hardest setting.
Okay.
Level 1, the baseline, was code plus a description of the bug. Levels 2 and 3 gave even more help, things like stacked traces, the error messages when a program crashes.
Like a breadcrumb trail to the crash site.
Exactly. Or patch diffs, which show exactly what code lines were changed to fix the bug.
And I assume more info helped.
Significantly, yeah. With the richest info, level 3, success rates jumped up to over 17% for reproducing bugs. But interestingly, level 0, just the code, while lowering reproduction rates, slightly increased the discovery of new vulnerabilities.
Because they had to explore more blindly.
Probably, yeah. More exploration, maybe stumbling onto things unexpectedly.
What about the complexity of the vulnerability itself, or the fix? Did the agent struggle more if the PPC needed was long or complicated?
Oh, absolutely. That was a major hurdle. If the proof of concept needed more than 100 bytes of input, which was true for almost 2/3 of the data set,
Yeah.
the success rate dropped below 8%. They really struggle with generating longer, more complex inputs needed for intricate vulnerabilities. It's hard to reason through those multi-step processes.
And how do they actually work? Is it just one try, or do they iterate, learn from mistakes?
Oh, they definitely iterate. They try things, see if it works, maybe tweak the input, try again. Most successes happen somewhere between 20 and 80 tries, or execution steps.
Okay, so they can learn a bit.
Yeah, but the flip side is almost half the runs just stopped. They hit the limit, around 90 or 100 steps, without succeeding. So they can get stuck on the harder problems, just spinning their wheels.
Okay, so looking at those initial low success rates, you might think, well, AI hackers aren't a threat yet. But you hinted there was a twist, something unexpected.
Right. This is the really fascinating part. Even though their overall success rate on known vulnerabilities was low, they still managed to find new, previously unknown vulnerabilities. 0 days.
Hold on. How does that work? If they struggle with known problems, how are they finding unknown ones?
It seems their sort of exploratory process, even when failing to find the target bug, can accidentally trigger other flaws. They might try an input that misses the known vulnerability but happens to hit a different unknown weak spot.
Okay, that's the aha moment. So what are the numbers? How many of these 0 days did they actually uncover?
So in the first round of tests, they generated 540 PoCs. They tested these against the latest patched versions of the software. 32 of those PoCs still cause crashes.
Crash the patched versions.
Yeah. After manual checking, they confirmed 9 unique new vulnerabilities across 6 different projects.
Wow. And they did more tests after that.
They did. They ran a bigger experiment with OpenHands and GPT 4.1 on the latest code from 431 projects. That triggered another 16 crashes, leading to 8 more confirmed unique vulnerabilities.
Okay, so adding it all up, what's the final count of these hidden flaws the AI dug up?
In total, they identified 17 vulnerabilities this way. And get this, 15 of those were confirmed 0 days. completely unknown before. The other two were unpatched but had been disclosed elsewhere.
15 0 days found by AI agents.
Ah.
That's significant. Were these specific types of bugs? Any patterns?
Yeah, they tended to be common vulnerability types, things like insufficient error handling, missing boundary checks, not checking if data fits where it's supposed to go, and also issues with excessive recursion, where a function calls itself too many times.
Can you give specific examples, like what kind of common flaws?
Sure. The breakdown was 4 out-of-bounds reads, 1 out-of-bounds write, 6 null pointer dereferences trying to use a pointer that points to nothing, and 4 stack overflows. These are all potentially serious issues.
Definitely. And I assume they disclosed these responses.
Oh, absolutely. They reported all the confirmed vulnerabilities to the project maintainers so they could be fixed. Standard procedure.
Okay, so we know what they found, but how do they do it? Can you walk us through an example? Give us a feel for the AI's process.
Yeah, there's a good case study. It was OpenHands using GPT 4.1 tasked with reproducing a bug in a function called readMNGimage, probably in some graphics library.
Okay.
So the agent started by basically using command line tools like grep and find to search through the code files, looking for relevant bits based on the bug description.
So it's navigating the file system, reading code.
Yeah.
Like a human developer might.
Exactly. It located the function, and it even seemed to understand the structure of the specific data format involved something called an MNGO chunk. But then it did something really clever.
Yeah.
It realized it needed a tool called XXD to look at binary data, and that tool wasn't installed in its environment. So it figured out how to install X itself and then used it.
Wait, it installed its own tools? That's
Yeah.
pretty sophisticated problem solving.
Yeah.
More than just code analysis.
Right. It adapted its environment. Then it built an initial PC. That first try didn't work, so it went back, analyzed why, and mutated the PC. In this case, it just added a null byte in the right place, and that triggered the targeted heap buffer overflow, iteration, and adaptation.
That's incredible. A multi-step process involving tool use and iterative refinement. Were there other advanced things they saw agents doing?
Definitely. Sometimes agents tried to actually build the software from source following the project's build instructions, like compiling the code themselves.
Wow.
And they weren't just generating simple inputs, they were seen writing actual Python or Bash scripts to act as more complex PayPacs. So quite versatile.
Okay, if they can do all that complex stuff, why the low overall success rate we talked about earlier? Where do they typically fail?
Well, several common patterns. Sometimes they just run out of time hitting that iteration limit without finding the solution.
Right, getting stuck.
Yeah. Other times, they kind of give up too early. They ask for human input when they get stuck instead of trying harder to figure it out themselves. And a big one was generating huge amounts of output, like printing an entire massive file to the console, which just overwhelmed their processing capacity, their context window, and caused errors.
Ah, okay. So information overload or just hitting a complexity wall. That makes sense. How does this AI approach compare to traditional fuzzing like that OSS fuzz you mentioned? Are they fundamentally different?
They are quite different, yeah. While they both involve testing inputs, fuzzers are all about quantity. OSS fuzz throws millions, maybe billions of mutated inputs at a program very efficiently.
Brute force, basically.
Kind of, yeah. Smart brute force, but still massive scale.
Yeah.
The AI agents, on the other hand, might only try, say, 10 different PoCs for a given vulnerability.
10 versus millions. So the AI is going for quality.
Exactly. It's using its reasoning ability to try and construct high-quality, targeted test cases. It seems better at understanding complex input rules or formats that fuzzers might struggle with. And the proof is in the pudding, right? Meaning the agents found 0 days that OSS fuzz, despite running constantly, had missed. It shows they aren't just a replacement for fuzzing, they're complementary. They find different kinds of bugs.
Okay, that's a really important takeaway. So, wrapping this up, CyberGym gives us this much-needed realistic benchmark.
Yeah.
And what we're seeing is, well, AI agents have limitations, for sure, especially with complex stuff, long bugs.
Better limitations.
But their ability to find actual 0 days, even now, that's a game changer.
It really is. And it underscores that dual-use nature, right? This tech can be incredibly powerful for defense, finding flaws before the bad guys do.
Right.
But the same capabilities could theoretically be used offensively, which is why research into making these agents safe, controllable, and aligned with defensive goals is just critical.
Absolutely. So the final thought then, if today's agents, with all their struggles, can still find 0 days that evade other methods, what happens when they get better? When they master that long context reasoning and get more specialized tools, what does that future cybersecurity landscape look like?
How do humans and AI work together or potentially against each other in that future?
That is definitely something to ponder, a fascinating glimpse into what's coming. Thanks for walking us through CyberGym today.
My pleasure. It's a really important piece of work.
Indeed. And thanks to all of you for joining us on the deep dive.